we have 15 minutes. So when you have 2 minutes and time's up, I'll let you guys know. So yeah, let's start. You are Technion, yeah, is it right pronunciation? Israel team that you are just a second upper grad, your upper grad team participate in manufacturing track. So welcome. Yeah, we are 2 judges present and there are 4 other judges online. And whenever you're ready, just let's start.
Okay. I guess we'll start then. Okay. Hello, everyone. Thank you for having us. We are iGEM Technion 2022, and we are very excited to introduce you to our iGEM project, Angel Roots. So, can any of you try and think, what do these 3 have in common? They are all traditional medicine, whose bioactive compounds are now widely used in the cosmeceutical industry, an industry that combines both cosmetics and pharmaceuticals together. We would like you to meet the newest member of this family, the Angelica gigas, a seasonal plant grown in Southeast Asia. Researchers have been trying to understand the root of its medicinal properties, and they might have found it, the curcin, a small hydrophobic molecule which is synthesized from phenylalanine in the plant. The curcin was found to be effective against many types of diseases: osteoporosis, diabetes, Alzheimer's, several types of cancer, but above all, it was found to be a leading candidate for the treatment of chemotherapy-induced alopecia. Alopecia refers to a complete or partial loss of hair. In order to understand the importance of hair for patients, we talked with Jaudat George Eid, formerly a senior social worker from the oncology department. He explained to us how hair is one of the last things patients feel they have a sense of control over, and how traumatizing it can be. If you look at this chart, these numbers speak for themselves, but we wanted to see it with our own eyes. So we teamed up with 2 non-profit organizations who assist children with cancer. We helped the first organize an event for the pediatric oncology department, and then we hosted the first ever iGEM Technion hair donation event. The donated hair can be used for wigs, and it was just great seeing everyone come together for a great cause. But thinking about wigs in a hot summer day in Israel made us understand that a solution was deeply needed. 2 other existing solutions are minoxidil, a drug taken orally, and cooling caps, but both were found to be ineffective in most cases. So by this point, you might be wondering to yourself, why isn't the curcin, the leading candidate, is on this list? And we were wondering just the same thing. Our team envisioned a hair care product containing the curcin. So we went ahead and did a market analysis. We discovered that 6.3 million patients annually are suffering from CIA. Based on this, we can estimate a market size of around $100 million. We then wanted to know how much the curcin we will need in such a product. So we conducted a skin permeability assay. We chose PAMPA, which is a cell-less assay, mainly due to its safety, but also low cost and efficiency. As you can see in the plot, we had 3 controls: low, medium, and high permeability control. The curcin behaved similarly to the low permeability control. And from this, we can learn 2 things. The first, the curcin does not penetrate too deep into the skin. And the second, we can use this information when we optimize a future formulation. So now we can look at the price, at the existing price of the curcin in the market, $100 for 1 milligram. And based on the market analysis and the permeability assay, and also similar products, we can conclude that the price reduction of 4 magnitudes is needed in order to introduce such a product to the market. So how can you do this? We can biomanufacture the curcin in bacterial cells. The curcin makes a good candidate for such manufacturing because it has a known anabolic pathway being a secondary metabolite. This will allow a safe, efficient, and cost-effective way to manufacture the curcin in large scales. So now you understand the motivation behind Angel Roots. And in order to discuss biomanufacturing, I invite Bara.
Thank you, Matan. And from here, let's look at the decursin pathway. This is the anabolic pathway of dicursin that is found in Angelica gigas plant. And we choose to start with the fifth metabolite, which is called amblyopheron. So talking about our biosynthesis pathway, we found 3 different enzymes that are responsible of turning amblyopheron to 7-dimethylseparosin, which is also called DMS, and then to dicursinol. So from here, by using a simple non-enzymatic esterification reaction, dicursinol is converted to dicursin, which is our desired molecule. So from here, let's zoom in a little to our first reaction. This reaction from amblyopheron to 7-dimethylseparosin is catalyzed by an enzyme called U6PT or prenyl transferase. This enzyme transfers a prenyl group from the donor DMA-PP to amblyopheron and turning it into DMS. So we aim to clone this gene under the RELR promoter together with the mTOR reporter gene, and we're still trying also to clone 3 other homologs to this gene. Our second reaction in the biosynthesis pathway from DMS to dicursinol is catalyzed by 2 different enzymes called SHIM-D and SHIM-E. They are both cytoplasmatic and originally found in Streptomyces strain. So as you can see here in this slide, SHIM-D catalyzes the reaction from DMS into an epoxide intermediate. From here, there are 2 options. With the presence of SHIM-E, this intermediate is converted to dicursinol, but with the absence of SHIM-E, this intermediate is spontaneously converted to a secondary unwanted metabolite called myrmezine. So in order to prevent this unwanted reaction, we modeled it. As you can see here in the left, this is the concentration of each metabolite over time, and you can see that there's a difference between the concentration of dicursinol in red and myrmezine in orange. This difference could be explained if we're looking at the second graph in the right side that shows the ratio between dicursinol and myrmezine versus the molar fraction of SHIM-E. So let's look at this example that shows when the molar fraction of SHIM-E is equal to 48% from the total recombinant enzymes in our system. The concentration of dicursinol and myrmezine is equal, meaning as this molar fraction increases, there is an increase also in the ratio in favor of dicursinol. So we can conclude from this that in order to have a higher concentration of dicursinol, we must have a sufficient amount of SHIM-E also. We then wanted to merge all of this conclusion in our genetic circuit design. And as you can see here, we cloned the SHIM-D under the lac regulation in order to control its expression, while SHIM-E is expressed constitutively. So after we designed our genetic circuit and we build it, according to the engineering success cycle, we have to test it. Thus, we conducted a qPCR test, as you can see here. The transcribed level of SHIM-D are higher than the negative control and lower than the positive one. The same thing in the case of SHIM-E, meaning all of our enzymes were transcribed. In addition to this, if we're looking at the fold change between the induced and non-induced system, we can see that the transcribed level of SHIM-D are really affected by the induction. And indeed, because SHIM-D is cloned under the lac regulation. So to sum up, this is how our biomanufacturing machine will look like. One bacterial strain that contains 2 plasmids, and these 2 plasmids express 3 recombinant enzymes. So by providing amblyopheron to this system, it will diffuse spontaneously through the cell membrane according to our modeling results and will be converted to dicursinol. Our following step was to quantify the quantity of dicursinol in our system, and thus we conducted a HPLC test, as you can see here, after we consulted with Professor Ayelet Fishman. This is the standard of dicursinol, and this is our sample. Unfortunately, as you can see here, we didn't get the specific peak at the desired retention time and wavelength. So we wanted to run other iterations with our samples by changing the incubation times with the metabolite, by changing the lysis techniques, or also the extraction method, but we didn't have the expertise to do this, and the HPLC test is time consuming. So if we are looking back at our framework, we still miss this check in the measurement. So in order to explain to you how we continued our project and how we wanted to measure our biomanufacturing product, please welcome Iser.
Thank you, Bala. So, as you've just seen in the previous slide, and as Bala explained, HPLC isn't perfect. And here you can see just some of the disadvantages of the HPLC system. These led us to develop our own method, the Aurocell system. It's a method for quantitative detection of metabolites using an organism's existing pathway, and it's based on a luciferase assay. And as you can see, the same disadvantages of the HPLC system have now become the advantages of the Aurocell system. And on our way of developing our quantification tool, we noticed an interesting phenomenon, which you can see here. The underlying mechanism of the Aurocell system is the hippo pathway. And on the left here, you can see one mode of it, the hippo off mode. In this mode, the YAPTAZ proteins translocate into the nucleus. They bind to the T transcription factor, bringing to expression of our reporter gene luciferase, giving us a bioluminescent signal. However, there's a second mode, the hippo on mode. And in this mode, the YAPTAZ proteins are degraded, meaning that they can't translocate into the nucleus. They don't bind to the T transcription factor, meaning we don't get an expression of our reporter gene, meaning there's no detectable bioluminescent signal. And we've seen from the literature that with the addition of dicursin, we're able to interfere with the hippo off mode, meaning that the previous bioluminescent signal that we detected will now disappear. And we theorized that with the addition of dicursin, we can also interfere with the hippo on mode, meaning that we will now be able to detect a bioluminescent signal. And that's precisely what we saw in our results. Here you can see the Aurocell system with different incubation times of dicursin. And here, following 1 hour of incubation, we can see that the cells not incubated with dicursin in orange, they have a much higher bioluminescent signal comparing to those cells that were incubated in blue, meaning that the dicursin caused a decrease in the detectable signal. However, as time goes on, at 3 and 10 hours, this gap closes. And by 16 hours, we can see that this trend is completely flipped, that the cells not incubated with dicursin, they have a lower bioluminescent signal, meaning that the dicursin increased the signal. And thus we concluded that at the 1 hour period, we were in the hippo off mode. And by 16 hours, we've made the transition to the hippo on mode of the cells. So now you've seen how dicursin interacts with the Aurocell system, but we can't reserve it only for ourselves. And here you can see many other molecules that impact the hippo pathway and could thus also be quantified using the Aurocell system. But it's not only a quantification tool, it's also a screening method. Any molecule that's able to impact the hippo pathway should be able to be detected using our Aurocell system. And one of such molecules is the crocin molecule being produced by the iGEM Latvia Riga team this year. It's their first time in iGEM, so we're happy to get to include them in our project. And here you can see the sample that they sent to us. And because crocin is able to impact the hippo pathway, we should be able to detect it using the Aurocell system. And so now, if we look back at our framework, you've seen the motivation for angel roots through the PAMPA assay. You've seen our successes on the biomanufacturing side with the transcription of shim E and D, and you've seen how we overcame the obstacles of HPLC through the Aurocell system and how we can now detect dicursin. And so now that you've seen where our project is at its current moment, we can now look into our future. We weren't satisfied with the yield that we were going to expect of dicursin, so we modeled a mutation of the shim E enzyme to hopefully increase the yield of dicursin compared to marmazine. Once we did that, we can then move into a larger scale to an industrial size. And for that, we modeled the fermentation to see the yield of dicursin that we can expect, as well as the cost associated with that. And for that, we consulted with Professor Yuval Shoam, who lent his expertise on the fermentation process. And following that, we can then move forward into preclinical screening to test the safety and efficacy of dicursin. And for that, we have our collaboration with the pharmacy company. They're a CRO company back in Israel that agreed to help us with the preclinical screening once we reach that stage. And so now you've seen the science side of our project, but now we want to look at how our project impacted the world, specifically through education, but not just education in a post-COVID-19 world, and a world that's kind of caught in between in-person and digital learning. So we want to incorporate both of those in our project. And on the left over here, you can see the in-person side with all the lessons that we gave. Specifically here, we had a lesson with Ukrainian refugees, as well as various high schools that we went into and taught about synthetic biology. And all of the lesson plans that we made were made suitable for people with ADHD. And we also published them online so future iGEM teams can teach the same lessons. And on the right side, you can see the digital projects, as well as those in the middle that had a foot in both worlds of the in-person and digital side. Speaking of which, we have the hallmark of our education, our virtual escape room. We published a escape room online and we sent it out to various iGEM teams. And here you can see the screenshot of the escape room. We also went into high schools and taught about synthetic biology and then had them attempt the escape room as well. And following the first few high schools that we visited, we were flooded with requests. Over 30 high schools reached out to us and asked us if we could come to their schools to teach about synthetic biology. Unfortunately, because of the physical distance and the time restraints, we weren't able to reach all of them in person. And so for those schools that we weren't, we held a Zoom meeting with the teachers from those schools so that we could teach them about synthetic biology and they could then pass it on to their students. And through both of those methods, through us teaching and through the Zoom, we were able to reach more than 600 students, which was truly astounding. We never thought we could reach that many students and teach them about synthetic biology. So now you've seen how our project impacted the world, and it wouldn't have been possible without our mentors that assisted us in every step of the way and lent us a hand whenever we needed it, as well as the companies that did the same. And so now you guys can understand, this is Angel Roots. This is our project. Thank you.
Thank you. Yeah, perfect timing. So online coaches, go ahead because they are here and we can go see them later. So you guys go ahead.
I had a really quick question. First of all, great presentation. That was awesome. I really like you guys' wiki. It looks really nice. So, you kind of cited the extraction of decursin from this plant, being costly and effective and polluting. And then I was just wondering, you picked this intermediate umbelliferone that you are, kind of starting the process with. Is this an intermediate that, is cheap and easy to get, or is this not just kind of, are you solving the problem of, this costly and polluting basically by going with this intermediate, if that makes sense?
Yeah, so actually, we chose to start with ampeliferone after we analyzed the prices of each metabolite and found that ampeliferone, it's the cheapest and the optimal point to start our project from.
Where did it come from? Yeah, and where does it come from? Do we get it from plants too, or?
No, it's by a synthesis,
Oh, okay.
by manufacturing.
I see. Chemical.
I also have just a simple question. I saw you talking about more about your human practice. How do you think majorly the human practice impacted your work?
So because our project touches such a sensitive subject, so we really wanted first to understand it from the point of view of the patients and not from the biomanufacturing side. So we contact like different organizations and we organized the hair event to see like the problem is still here and the solutions are still far behind, like wigs are not efficient. And as we talked with the patients themselves, it helps us to better understand like the solution is needed. And that's what gives us the motivation to go on with this project.
Okay, just about the shampoo. How did you come to like rule out that maybe the shampoo would be the better option to deliver your product?
So we also consulted with Dr. George Id, which is a former social worker that works with the oncology department in Israel. And with the conversation with him, we understood that the solution shouldn't be like a drug or something. It should be really friendly like to the patients themselves. And we also, with his help, conducted a survey. And we asked the patient themselves what will they want to use, and they said like a shampoo or cream like product will be more suitable.
Thank you.
Online judges.
I have a question about the enzyme design part. I see your wiki. You have discussed that you have designed the Chimera 1 and Chimera 2 enzyme. Can you explain how did you design them?
So, can you hear me?
Yes.
Any specific questions regarding the design, or just to lay out the process?
Maybe lay out the process. Yeah.
Yeah. So basically, we identified at first 4 homologs of an enzyme, which is a U6PT called PCPT. It comes from parsley. And after a short literature review, we feared that it might not be expressed in bacteria because there was no history of this enzyme being expressed in yeast, because it's a plant enzyme. So we went to online databases and identified enzymes that were expressed in yeast, which prompted us to feel more comfortable in attempting to clone them in bacteria. But they had different parts of our reaction, and we wanted to combine them. So the reaction, the prenylation, consists of a donor molecule and an acceptor molecule. And we took we had one enzyme which worked on the correct donor, and the other enzyme, but the wrong acceptor, and another enzyme which had the wrong donor, but the right acceptor. And we identified the domain responsible for binding each part of the process, either the donor or the acceptor, and we made a switch. If you want, I can elaborate on how we identified it, but that's in general the chain of thought.
Okay, thank you.
We have
So
5 minutes.
something small about, you talked about the oral cell, right? The alternative method for metabolite extraction. About that method that you said you had tried HPLC. Did you try several methods of HPLC before you, several methods of extraction? I know the other methods, how to optimize extraction of plant metabolites. So I like that you came up with the new innovation of doing it yourself to see that. So previously, before I know you learned a lot. So previously, did you try more than one method for you to opt for the oral cell? Do you try the more than one method of extraction?
So a little clarification, the oral cell method isn't an extraction method, it's a detection method. So it...
yeah, then I get you. So you use it for detection after extraction. Is that right?
For detection, not for extraction.
Okay.
Yeah, online judges, go ahead if you have question. Otherwise, I have a lot. So, Yili, do you have question maybe?
Yes, I would like to ask you first, a very good presentation and very nice project. And I would like to know, what would you change about your project if you had more time, or if you could start all over again, or what could you have avoided to do in the first place? Yeah.
HPLC.
So if we're talking about the synthetic part of the project, specifically the U6PT enzymes. So we worked in parallel with 4 homologs and 2 chimeras, which Amit previously talked about. The design included a reporter gene, and between the U6PT and the reporter gene, P2A sequence, a ribosomal cleavage sequence. This design, I think, made the process a little bit difficult for us and time consuming. I think for future plans, we would want to change the design for the U6PT. Maybe we won't use a reporter gene. We will use a his tag in order to detect and maybe quantify the levels of expression of this enzyme. And from there, just carry on the process with the rest of the enzymes, the SHIM-E and SHIM-D, along with the oral cell method.
Okay, great. Thank you.
Any more question from online judges?
Yes, I have a quick question. So first, good job. I really like your project. So my question is, since your product is for cancer patients, so you should make it very safe to use. How are you planning to do this? Like to be strong enough to have the required result, but also to be safe for the immune system and for other internal systems.
Yeah, that was also something we thought about. So the main thing we did in that region is, and actually the Pampa assay, just to make sure it does not penetrate too deep into the skin and only reaches the scalp and the relevant regions. And this is something also the collaboration with Pharmaseed has a great importance in, because they have the experience in the screening process and all of that, and testing how it affects and all of stuff like that. So it's very important when you design something like that to also take safety into account.
Okay, thank you.
Yeah. Any last question? Otherwise, I will come to your interactive booth for a few more questions. But now is the time to transition for the next team. Thank you so much. Great job.